current loop as a magnetic dipole and its dipole moment. In the last lecture, we said that a bar magnet is a dipole or magnetic dipole, and we had said its dipole moment. Similarly, we here calculate the dipole moment of a circular coil, because a circular coil or a current carrying loop is also a magnetic dipole. It means that it will have south pole and north pole. Okay, so here I have considered a circular coil, that is my loop. Okay, current carrying loop, and this is my current I flowing in this direction, and this loop is perpendicular to the plane of the board. Okay, so this loop is perpendicular to the plane of the board. It means that this is like this. Okay, isn't it? If it is like this, then they are parallel, but it is like this, it means that they are what? Perpendicular. Okay, angle between this plane and this is my 90 degree. So let us find first the magnetic field produced by this current carrying circular loop. Okay, not the quality, not the quantitative using Biot-Savart law, only the qualitative. Okay, we have already done this in the chapter 4 also. So which law we use? We use a right hand thumb rule. Okay, right hand thumb rule. So this is the direction of current, like this. So in this part, the current is going inside. So I have to hold it in such a way that the thumb represents the direction of current. So like this, and whenever I hold it, the magnetic field is going downward and it is making a loop here, isn't it? It will make a loop. So there will be a many loop like this. Now let me hold it here. Here the direction of current is in this direction. So this thumb should come like this and hold it. At this point also the magnetic field is going inside, isn't it? This is thumb, isn't it? So going inside and coming outside, very inside like this. Now I will hold it here, this part, because here the current is going in this direction. So I have to point the thumb there. Again what I do, in this way I will hold it and make it like that. At this ring also the magnetic field is going inside. Here also the magnetic field is going inside. Okay, now I will hold it here. I will hold it here, and here the current is coming towards you. This is the current and magnetic field going inside. So it means that at each and every point the magnetic field is going inside. Okay, so here I will make a straight line, and this is my magnetic field, and here what it is going, it is going inside. Okay, and coming outside, and it is making what? A loop like this. Okay, which I am not going to draw it here. So this is like this. So here is going inside, right? Here is also going inside. Each and every point the magnetic field is going inside, and here also it is going inside, and from this part it is going outside, and this is inside. Okay, so this is how, and remember this is making a loop. Okay, everywhere it is making a loop. Now which part will be its south pole and which part will it be my north pole? So to understand this, first I will go to this diagram. So here I will consider a south pole here, and this is my north pole. This is my bar magnet. Now what happens in the bar magnet? So there will be a uniform magnetic field inside the bar magnet. Okay, we know everything about this. Now in bar magnet, north pole से south pole पर क्या होगा? All the magnetic field will go in this direction, and inside it is going from south pole to north pole. Similarly, north pole to south pole. Okay, this is too big now. North pole to south pole. So this is the direction of magnetic field. Magnetic field, this is my north pole. Here it is going in this fashion, it is going in this fashion, north pole and south pole. Coming out from north pole, coming out from north pole in this fashion, and coming into the south pole. Okay, south pole entering in the south pole, outgoing from the north pole, and inside the bar magnet, the magnetic field direction is from south pole to north pole, right? So here also it is direction of the magnetic field is going from upside to the downside. Where is going? It is going from upside to the downside like this. So if it is my a circular coil in this fashion, the magnetic field is going from here, passing through the thickness of this wire and getting out. Okay, so it is going from upside and getting outside like that. Can you see this? So this is how it looks like. Magnetic field going from this part and coming out from this part. Okay, like going, coming, and you know that from where the magnetic field goes in, that is my south pole. Okay, goes in, and from where the magnetic field comes out, that is my north pole. Okay, of bar magnet. It means that from this part it is going downward. It means that the upper part is my south pole and lower part is my north pole. Understood? It means that this has got a dipole. Okay? So current loop. Current loop is equivalent to magnetic dipole. Magnetic dipole. Why it is equivalent? Because what is magnetic dipole? Dipole means it has got north pole and south pole. Okay, magnetic north pole and magnetic south pole. Now here we got that this part is south pole and this part is north pole. So this has got what? A dipole moment or magnetic moment. Okay. I have already said it. You can also call this as magnetic dipole moment or simply magnetic moment. Okay, so it has got the magnetic moment or magnetic dipole moment because there is south pole and north pole. Then this coil is also a magnet because south pole and north pole is also present in the bar magnet. Then this is simply a bar magnet. So wherever you see a current carrying loop, then you can say that that is my magnet. You can always say that is my magnet. Now say there is one more easy way to find which part is south pole and which part is north pole for a current carrying loop. Okay. So for this I will consider this loop here. So this is my loop. I will consider a loop, this loop, and let the direction of current is in this direction. Now tell me this is which direction? It is going tick 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 tick. So this is my anti-clockwise. Anti-clockwise. The direction of current is anti-clockwise. So it is going in this direction. It is going in this direction. Isn't it? So it is going in this direction. So I will join this two line and this is my N, isn't it? This look like a N in N, this and this, isn't it? So this is like this. And it means that if the current is in anti-clockwise direction, then that side is my north pole. North pole, please remember. Okay, if there is a coil like this, that is my coil loop, and if it is the current is in this direction, that is anti-clockwise direction, then you know that whenever there is an anti-clockwise direction, then this part will be my north pole. This part will be my north pole. Okay, so this part is my north pole because from this diagram. Now in the next diagram, let me consider another diagram here. So this is my another diagram. Now it was going in this direction. Now, okay, I will take this in this direction. Okay, so it was in this direction, I will take this in this direction. So what is happening here, this is in this direction, going in this direction, and this is coming in this direction, right? And this is my which direction? Tick, tick, tick. It is my clockwise direction. Very easy, okay? And I will join this, then it's look like a S. It means that if the direction of the current is clockwise, then this will look like a north pole. Not north pole, it is S, so this is south pole. Okay, always remember, for clockwise it is south pole, for anti-clockwise this is north pole. Clockwise south pole, anti-clockwise north pole. Okay, so if you have this, now the direction of current is clockwise, tick, 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 tick. Whenever you look at from here, tick, 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 clockwise, south pole. So this part will look like a south pole. Okay. Now if you see here with this two diagram, now it is like this. Now at this point, the direction of current is going inside, isn't it? Now whenever I look it from above, it is going in this direction. Which direction is this? Tick, 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 clockwise direction. If I look at from here, then if it is clockwise, then it should be a south pole. It means that whenever I look at from above, south pole will be this part because this is in this direction, clockwise direction. Okay, this is in clockwise direction. Looking from above, I will see the direction of current in clockwise direction. So this is my south pole. Now if I do it like this, okay, if I do it like this, again the current is in the same direction like this, but which direction is this one? If I look at this one, this is my tick, 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 isn't it? Which direction? It is my anti-clockwise, so it will look like a north pole. Okay, I will explain here also. So if you see here, let me have this. So this is my direction of the current. From your side, what is the direction of the current? It is coming, it's in this direction. From your side, it is in this direction. So from your side, this is in clockwise, tick, tick, tick. From your side, it is in clockwise, tick, tick, tick. That is, this side will be which part? South pole, this part, because it is in this direction. But the same for me, it is going in this direction. For me, the clockwise direction should be in this direction, but this is my anti-clockwise. For me, it is my anti-clockwise direction. For anti-clockwise direction, this part will be my north pole. It means that this is north and that is south. This is how you can have the north pole and south pole of a current loop. Okay. Now, a special one thing is that the definition of magnetic dipole and its dipole moment. Okay. So now what I do is, the definition is, it is defined as, okay, dipole moment, magnetic moment, magnetic dipole moment is defined as m vector is equal to current I into area vector. So this is the definition, and I am already said in the last lecture, this dipole you can make it silent. If you make it silent, then it will become magnetic moment, or you can also say magnetic dipole moment. Now if there are n number of strands of coil, how many numbers? N number of strands of coil, then this m will be equal to how much? For n number of strands, this will be n I a vector. Okay, So dipole moment of a coil is NIA. That is N is, what is N? Is number of dipole, number of turns. Okay. Now this we got how much? We got M vector is equal to N I A vector, and this A is my area vector. Okay. So area I will tell you later in few minutes. Now magnetic dipole moment is my direction. It is my it is a vector quantity, then it must have the direction. And again the direction is from south pole to north pole. So for this it is south pole, this is north pole, so this is the direction of magnetic dipole moment. Okay. Now if I give you one question like this, again same thing, but here it is coming in this direction, outside it is going inside, just opposite to this one, then all the magnetic field will look like same, but in this direction, this direction. Okay, it is not so difficult. So from where it is going, below side, so this is my south pole. From where it is coming out, it is from this side. So jahan dekhi paschat त्यो भयो south pole, jahan dekhi निक्लिन्छ त्यो भयो north pole. So direction is from south pole to north pole. कसको direction? The direction of magnetic moment or magnetic dipole moment. So this is the direction of magnetic dipole moment. Okay, so this is all about your direction also. Okay, now I have said the loop. Okay, loop. This loop could be a circle. This loop could be a square. This loop could be a rectangle. So many things. Okay, hexagonal, pentagonal, etc. So what is the area now? This area is the area of this loop. For circle, this will be pi r square. Okay, if it is a square, then it should be a side square. Area is side square. And rectangle, length into breadth, and so many things. So this should be a loop. It is not necessary that it has to be a circular loop. It could be rectangular loop, it could be square loop, etc. And area is the area of that particular loop. Here the area will be my pi r square, because I have considered a circular loop. So this is my definition of dipole moment of a current loop. We said that a current loop is a magnetic dipole. Why? Because there is south pole and north pole. And if it has got south pole and north pole, we define that the magnetic moment is M equal to I into A. And for n number of turns, there will be M equal to NIA. Okay, thank you.